Okay, so hello everybody. I wish everything is going fine. So let's have a look where we stopped let's have a look at our last week's notes. I just want to see where we stopped. Okay, so we had the Cramer's rule, which can be used to solve the system of linear equations. And we did also the LU decomposition for the solution of a certain system. And we noticed that if we did everything in a correct manner, in a careful way, as we were obtaining the U matrix, so the first thing we learned, it was how to obtain the upper triangular matrix using the reduced row, not the reduced row echelon forms, but by using elementary row operations. So by using the elementary row operations, we could get the U. But if we write every expression as Rj star is equal to Rj minus lambda Ri, these numbers, we notice that these numbers, they are part of this lower triangular matrix L, which will be one of the decomposed components. Now, I guess we did an example using the LU decomposition. So I think we covered this execution time. We said I think we covered these examples, and we said that whenever we try to solve these systems, we had a problem. Sometimes we could observe that in order this lambda that we see in this expression, this is equal to Rj minus a. Let me think. So we want to make 0 here in the rows j, in the jth row. This is j I over aii, I think, ri. So the issue is that sometimes we might get a matrix where the pivot element is 0. Pivot element 0 would be a case such as when a is equal to, but I guess for the moment, you're looking at probably this is better for the moment, so we are not showing much on the PowerPoint. So this is how we will exchange the rows, but sometimes we might have this would be 0, 2 through 3 minus 2. So if we have such a matrix, we would have a problem because we would have a division by 0. So we don't like this one. And in order to eliminate such a problem, we use pivoting. And what pivoting does, it converts, so we can switch the second row with the first row. And as we are going to see this one again in the iterative techniques, the pivoting is used also for exchanging of the rows. It can be used also to make a matrix to converge faster, or even to converge at all. So if a matrix is not in some specific shape, it will not converge. So today we're going to define the concept of diagonal dominance of matrices. So yes, we start. We were talking about these last time, and let's go back to this for a moment. So if we use Gaussian, naive Gaussian, we observe that sometimes we find no solution. But if we use the Gauss pivoting, it's Gauss P, and these codes, I think we shared these together. And we went over these examples, and we observed that we can have, for these systems, if we change only one element, so I think we went over these last time, just by changing a specific element in the matrix, we could have a matrix from having no solution to a matrix that can have an infinite number of solutions. Whenever we write down an algorithm, we can always, if we write a code for it, we can always count the number of steps that are needed to solve the problem, which would relate to the computational complexity of a certain algorithm. So we can always solve systems of equations using direct techniques, but if we write a well-structured algorithm to run it on a computer, often we might have the size of the problems that we want to deal, it might be so large that at some specific threshold value, the computational complexity or the runtime can be a critical aspect. Then we really need to take care of how many operations we need for each step. Now we said that we have direct method and iterative methods. So direct methods, we had, okay, so these are clearly explained here. We had AX is equal to B. We convert the matrix, we get the upper triangular matrix. Or the AX equal to B, it can be written as LU times X is equal to B, and so on. And I think we stopped last time at the LU decomposition. So LU decomposition, this is how the F, so what is F in this slide is the lambda that I wrote on the board. Let's move fast here. This would be the upper triangular matrix. This F or these lambdas that we find, they would be written in the lower part of the L matrix, the lower triangular matrix. And this is how we run these. Here we have an example. I don't remember if we did this one last time, but if we didn't, you can do this on your own. The matrices you can copy paste from here. You can copy paste them in any programming language that you would like. And apparently, this example given in this slide, it can have a solution versus not a solution because of it looks like the matrix A, the A11 element is a 0, which means that we cannot make the 0, the 2, the 3, and the 2, the 4, and the 6, which is A21, A31, and A41 elements of the 4x4 matrix. Now, we have a different type of decomposition, which is called the Choleski decomposition. And what this Choleski decomposition does, this is so this Choleski decomposition, let me get another. If you cannot see the board because of the quality of the pen, please just remind me or tell me that you can see it. So Choleski decomposition, as we can see in this slide, for any system which is AX is equal to B, we can convert this one into an upper triangular matrix transpose times the matrix U, the upper itself, X is equal to B. And for this, we have the so I guess in the previous slide we just saw that we have a certain expression of how to find the, let me get so for any matrix that we want to represent it like this, so we know that an upper triangular matrix, it would be a matrix which is 0, 0, this can be A11, A12, A13, A22, 0, A23, A33. This would be the upper triangular matrix. Its transpose, it's going to be something like here, the transpose of this one will be A11, 0, 0. and so on. And as you can see from here, we can even let me check something in the settings. We can improve something done. Okay, so here, this A12, this will come here, A12, A13, and as you can see from here, because of several reasons, we want the matrix A has to be a symmetric matrix. Because the same multiplication will be used to get A23 or A32. Okay, so any matrix which is symmetric, that is a candidate, or that's a matrix for which we can use Choleski decomposition to solve it. But now, this is also not complete for a simple reason that if we can see from here, this is U transpose, and this is the U, and this whole thing would be equal to a matrix A, which would be here. Sorry, that's not A. Let's assign this U because these are the upper triangular matrix. So let this be these elements U. I apologize for this one, but here we have A11, A12, A13, and so on. So if we look just at the first element, how do we get this A11? We get this one by multiplying the first row with the first column, okay? And from here, we see that U11 squared is equal to A11. So any one of us can notice that this element, which is, so this is the unknown element, this is going to be equal to the square root of A11. Now, we want to work with real numbers in this domain, which means that we wish that this matrix A, this is symmetric, that's the first constraint, so this should be symmetric, and it should also be positive definite. Positive definite. So these two conditions have to be fulfilled for us to get the Choleski decomposition. Now, we showed this one in the slide before a while, and the expression that we need to use, so the formulas to find these elements, they are as follows. Ljj, this is going to be equal to the square root of Ajj minus the summation of the k, it's from 1 to j, so this is to j minus 1 of Ljk, okay, so I have the summation term, but this has to be squared, this is it, and then this is for the diagonal terms. Apparently diagonal terms are expressed like this, then the off diagonal terms will be like this, Lij is equal to, we have Aij minus the summation of the k1 to j minus 1, Lik, Ljk over Ljj times 1 over Ljj. So these are the two expressions that we can use to find the diagonal terms and the off-diagonal terms of this unknown matrix. So let's look at one example. Let's assume that we have this matrix A, which is equal to 4 minus 2, 2 minus 2, 2 minus 4, 2 minus 4, 11. So with this matrix, we move on and we try to use these two formulas to find all the elements. So this A, we want to write this one as a product of a lower triangular matrix and an upper triangular matrix, but these two are transposes of each other. So this is, or we can write this one also as, this is the U transpose times U, or similarly, let me add also this, A transpose is equal to A, because this is a symmetric matrix. So this means that these elements with symmetric with respect to the diagonal of the matrix, they are equal. So now, let's try to get all these terms. So the first term that we can try to go for is, let's check the L11. So the element, if we set J equal to 1, the element L11, we look at this expression. It is going to be equal to the square root of A11, okay, minus the summation, so the summation term from K1 up to J minus 1. But now J is 1. 1 minus 1, this goes to 0. Okay, we run this to 0. And we get Ljk all squared. Okay, this is what we get. But then, well, J is 1, but we can keep it like this. Since the summation of the terms is from K1 to K to 0, this does not make sense. So this means that we don't really have this. Okay. So L11 is going to be equal to the square root of A11. We get this from the A, so this is square root of 4, we get a 2. Okay, so we found the first element. Then the next element we can go for is to find the L22. So let's set, so let's set J equal to 2. And let's go for L22. L22, it will have, we find again the same expression. We get the square root of, in this expression, AJJ is equal to 2 minus the summation of from K equal to 1 up to J minus 1. Now J is 2, minus 1 is 1, which means that at least we're going to get one term out of this expression, and we multiply this with JL. Actually, when J is fixed, we can write here J, it can be 2, and the K, it looks like we can write the general expression, but since K is from 1 to 1, let's write this 2, 1 squared, okay? Then this will be all. This is equal to, but now let's have a look here. Equal to, we know it already. And let me see what part of the board I can make use of to write the results. So we find that L11, it was 2. This is going to be 0 for sure, we know that. And we are going after L22. But we don't know L21, okay? So since we don't know L21, let's try to use this expression to find the L21 and to insert it here, because this is the only thing we know so far. So then, let's write here, to get the L21, that means that we will have, in L21, we have I is equal to 2, and J is equal to 1. J is equal to 1. Because this is Lij, and this L21 will be equal to Aij, which means it's from here, Aij, we'll get here A21 minus, we have to sum over the terms from, this is K1 to J minus 1. Now J is 1. J1 minus 1, that will be the upper boundary of the summation term, we get from K0 to 1, which means that this term, we will not have it, because this summation will go from 1 to 0, which does not make much sense. So we can keep this out immediately. Or we can keep this, so we get only this divided by Ljj. Ljj, let's see what the Ljj is. What is J? It's 1, so this is L11. So this is equal, L11, we know it, we found it here to be 2. So A21, which is equal to the second row, first column, this is minus 2, divided by 2, we get 1. Sorry, minus 1. So we get L21, it's equal to minus 1 here. And now that we know this L21, we can insert it here, and we get the square root of A22 is this 2 minus since we have only one term here, okay, this is the summation from 1 to 1, let's remove this summation term completely, and we get minus the L21 square. L21 equals minus 1, this means minus 1 square, 2 minus 1, this is equal to 1, okay? So L22, we get 1 here, and this is 0. So we found 3 terms, we need 3 more. We need this, and this to find the lower triangular matrix. Now, the next term we can go after, it's L31. L31, we can use so L31, this means that I is equal to 3, J is equal to 1, and this is going to be equal to Aij, this is A31, minus here, K, the summation will go from K is equal to 1 to J minus 1. Now J is 1, minus 1, 0. This means that this term, we can assume that we don't have it at all. And then this means that we have to divide this one, we have to multiply with Ljj, which is L11, which we get equal to A31. A31 is this 2 here. So we get 2 over L11, apparently we get 2 here. Over 2, we get 1. So L31 is 1 here, okay? We have 2 more numbers to find, and we can look for L32. L32 So L32, we look again, we go after this expression, that means that I is equal to 3, I is equal to 3, and J is equal to 2, and this is equal to Aij, which means that A32 minus the summation of K is from 1 to J minus 1. J is 2, minus 1 is 1. So actually we have only one term here. We don't have to sum up too many. And this is Lik. Li is 3, K is 1, times Ljk. J is 2, and K is 1, 2, 1. Okay? So we get this expression times 1 over Ljj. This is L22. Now, this whole thing is equal to, this is equal to, let's do this like this. We have A32 minus 4. This is minus 4 minus L31. L31, we found it here, minus 1 times L21. L21, it's minus 1 times minus 1 times 1 over L22. L22 is 1, so this whole thing is minus 4. Minus 4 plus 1, we get minus 3. So we get here minus 3. It goes here. Then the very last element is the L. This is the L33. The L33, we have this here. This is going to be equal to the complete square root of A33 minus the summation, which is k equal to 1 up to j minus 1. J is 3 here, minus 1 we get up to 2. So we're going to have two terms over there, and we have the ljk square. Ljk square is going to be ljk square. So the first j is 3, and the k will be k is equal to 1, 2. So this will be the combinations of k. So we have minus ljk, which is minus L3, 1 square, and but since this is a summation, so the summation term is L3, 1 square plus L3, 2 square. Okay, so if we, so this summation, this is what it means. So if, since we wrote both terms, we can write it, we can keep it like this, and this is equal to, so this is equal to A33. Let me just see what you can, the last part of the board. A33, it was 11, so this is equal to the square root of 11 minus the L31 square. L31, it's 1 square, plus L32, it's minus 3 square, minus 3 square. This whole thing is equal to 11 minus 1 plus 9, 10, 11 minus 10, it's 1. Okay? So L33, we get equal to 1. So this was the last element. So this is how we can use the Choleski decomposition. And the idea then is, since we found this this Choleski, this decomposition of the matrix A, we can say that the A itself is going to be equal to, so since we wrote these, and erasing this just means that we just need to go backwards in the recordings of the classroom. But then we get the following. We get that the matrix A, it should be equal to this 2, 0, 0, minus 1, 1, 0, 1, minus 3, 1. We multiply this one with the transpose of what this is. So the first column, it becomes a row, which is 2 minus 1, 1. The second column, it becomes a row, which is 0, 1, minus 3. And the third column, it becomes a third row, which is 0, 0, 1. So these two, these are equal to a matrix A, which is this matrix A here. Now, this is how the Choleski decomposition can be written. We just spend a couple of, now we can have a look. What am I doing? Present your screen. No. Reconnect. So if we use A, the A that we had on the board, which you have in your notes, it's something like 4 minus 2, 2, minus 2, 2, minus 2 to 4, minus 2 to 4, and 2 minus 4, 11, 2 minus 4, 11. So this is the A, and we can find the matrix U, which is equal to chol A. Okay, so there is a chol must be positive definite. Apparently we made a mistake when we entered the matrix. Yes, we did. So the matrix A that we use in the example we just solved, the matrix A, it was symmetric. So apparently we made a mistake. This is minus 2, 2, minus 4. We're missing a minus 4 here. So you see that it wanted the input matrix to be positive definite because it's defined for real numbers if you want to solve it. So it looks like this matrix A here, now this is symmetric. So this is probably, this is going to work. So that's what we get. So it looks like the U is the upper triangular matrix, which was here on the board. Okay, which here we got the lower one, but the upper triangular matrix is this one. And here, with this single comma, we get the transpose. So, wait a second. So that's A, that's U transpose. And this means that any U transpose, if we multiply this with the U, we get the A. So that's the answer. If we compare these two, they are the same thing. Okay, so this was how the Choleski decomposition can be used. So this is the matrix A, this is the L that we got, and we can, here we have another example, and we can try to solve the system. So this is Choleski decomposition. Let me have a, yeah, probably we can pass this fast. So let me see what is the next. So if we get this A, and if we paste this here, this is the matrix A, and this is the B, the vector B. So that's the A and the B. And if we want to solve this system, which is AX is equal to B, we can use either one of these functions here. So let's have a look here. What is this? X is equal to Gauss AB. So let's say the answer is equal to Gauss, pivot Gauss, using the input of A and B. And it looks like the answer is a half, a -1, and 3/2. So the answer is here actually, which is a half, -1, and 1/2, 3/2, if we use this B. Now, this matrix A that we have, we can even calculate a matrix UU, which is equal to the Choleski decomposition of the given A, and we get this upper triangular matrix full of ones, okay? And we can even, we can try to solve this, let's say. So we have that UU transpose. Let's assume that UU transpose is equal to UU like this, okay? So what this is the lower triangular matrix. Now let's assume for a moment that we want to use, now if you have a pen and paper, you can follow what we'll try to do, but let's assume that, I'm sure that since you're looking at the screen, probably you don't see all of the board, but here we have A times X, this is equal to B. Now this A, this is equal to this is the upper triangular matrix T transpose times the UU, the upper triangular matrix, times X, this is equal to B. Now let's assume that this is Y, and we have this UU transpose times a vector Y, this is a vector Y, this is equal to B, which means that here, in here, if we write here UU transpose, using the B, we get this solution, 1, 0.5, and 1.5. So here, we find that this unknown, vector Y, this is equal to, we get this is equal to 1, 0.5, and 1.5. But now this Y here, this solution, it's equal to this term here, okay? So this one in red, it's really substituting this Y here, which is this Y here. So, but let's see the initial unknown for us that we were looking for, and let's just stop presenting here. We can have a look. So this was the problem. We're trying to solve this system. We decompose the A in these two matrices, and they were good-looking ones. They were full of ones. The one everywhere, and the rest was 0. So we found this Y, and now the equation, it transforms into this form. The UU matrix, which is a matrix here, times this Y, which is 1, 0.5, and 1.5. This is equal to what? Okay, that's a mistake. This was, sorry, this is this matrix UU times X, which is the initial unknown of our system, this is equal to Y, because this term, we wrote this as Y, which is 1, 0.5, and 1.5. So that we know what this U is. The U actually, we can write this is 1, 1, 1, 1, 0, 0, 1. This is multiplying some unknown vector A, B, C. And we want to solve this one using Gaussian elimination or any other technique. So the ABC is unknown for us, which means that if we go back to where we were here, okay, cannot see. Okay, so this means that we have the UU matrix, and the answer vector, it's the X that is here, okay? So let's say that Y is equal to this X, just to keep this as a variable. Are we still okay? That's 1, 0.5, 1.5. And then in the Gauss solution, we're going to use this UU. We apply the Y, and it looks at the answer, it's 0.5, 1, 1.5. So the final answer to this system is the following. So the solution of this problem using Choleski decomposition is that the A that was given on the slide, this was the system, we had the B, and it looks like the final solution, it's equal to, let me read it from the slide, it's 0.5, minus 1, and 3 over 2. Okay, so this is just one small exercise or small example. So if we go back here, let's see what we get. This is a Choleski decomposition, that's an example. And then I had a couple of questions by email regarding the homeworks which was dealing with the convergence problem. And I just wanted, maybe I just put a couple of slides here so that we can have a look of how a possible answer could be formulated. So here, this is the code or something that I put together where I'm going to search for trying to solve the function using the Newton-Raphson method to find the root for the specific function, which in this case, if we go here, so the function which apparently is this one, cosine x minus x sine x. So apparently the function is y is equal to cosine x minus x sine x minus 1, and x sine x minus 1. So this is the function, and then we need to know also the derivative of this function, the dy, because the derivative of cosine x is equal to, is this what it is, cosine x? So the derivative, which is here, the d function 1, it's x, no, actually, sorry, I cannot see it very well here. Apparently I had, no, the function is this one. I was wrong. So this is x. Apparently this is the derivative of the function. And meanwhile, let me check whether I'm sharing the screen. Okay, I think I'm sharing the screen, right? Okay, so you cannot see much of the board. So apparently this is the derivative of the function. And the function itself, the y, this is equal to x cosine x minus x. X cosine x minus x. So we want to find the zeros of this function. And then we notice from if we draw the graph, we can see that this has periodic solutions. And the solutions, periodic solutions of this function, they are multiples of 2 pi. Okay, so the one solution is 0, the other one is 6.28, the other one is so the solutions here, which means that the intersections with the x-axis, they happen at x, which is equal to n times 2 pi. So whenever we try to find a solution, the reason that we wanted to give this as a homework, if this was going from 0 to 6, we wanted to see, so if we are in a certain range, we might be expecting that this n, where this converges, is going to be something 0, as we move step by step, okay? And then probably, the next, after some time, the convergence could be when n is equal to 1, okay? So, most probably, sama afër, për shembull, nëse jemi afër kësaj zgjidhjes, çfarë do lloj vlerë fillestare që mund t'japim, me shumë mundësi ne do prisnim që konvergjenca të ishte të 0, në 0 ose 6.28. Sa e vjen kjo? Një dhe 0, tjetër do jetë 6.28, e kështu me radhë. Dhe ndërkohë që jemi afër rënjes tjetër, ndoshta ne mund prisnim që vlerët e x-it që janë në afërsitë të asaj, nëhet në dalë fillim 0, paset në dalë 1, paset 2, 3, e kështu me radhë. Pra ndërkohë që ne kemi këtë hipotezë, ne mund të shkojmë dhe mund shikojmë për shembull se çfarë gjejmë, ndërkohë që ndryshojmë të nën. Kjo ishte për shembull këtë formulimin, këtë kodin e vogël që kemi përdorur, këtu për shembull po shikojmë, duket që nëse ne skanojmë nga 3 që kemi tune, se nuk e dalë. Ne pozicionojmë nga 0 deri tek 6, duke bërë hapa me 0.2, dhe duket sikur problemi jon konvergjon gjithmonë tek qëndron për një kohë gjatë tek 0, so we get a 0 continuously, then at some specific value it jumps way back to -6, and then for some in the next step by a plus 0.2 it jumps to 6 and then it stays at 2. Okay, so that's something which could be, so it looks like this can be seen also from this graph. So the value, it stays always 0, it goes -6, 6, 2. Okay, so we see a step function here, but we have this abrupt change. So the solution, it's way back, it's forwarded to the front. So if we do a change, if we are a little more, we use smaller steps here, and if we run this, we observe that we see much more changes in the values. Let's see what changes we see. It looks like for a wide range, for many values, it always keeps converging at 0. Okay, so we are in the proximity of 0. Then after some time, we see that it jumps way back to -50. And this -50, that means that the solution is -50 times 2 pi and so on. So then it goes to -2, -2. Then we see some oscillations here, which goes way back to -38. It comes back to 78. So imagine for a moment that the solution in the x-axis, if you have the x-axis drawn, it will go way back and then way on the front. So it looks like very small changes in the values which we are providing. We can see huge jumps. Now, this is something that once you write this one, it will be a good exercise for you to see what happens. So some results here, we have shown here the results of the n, and you can also check, and we can observe that if we use a delta x 10 to the power -4, the convergence, it even jumps to 32,000, okay? Or no, there's even a case when 93,000 n. So it looks like it's really going to converge to a 0 within the error bar that we put, but it's going to be something like 10,000. No, what is this? Not 10,000, around 93,000. So this is how much these things can jump if we use the step size in the, and let's not forget, this step size, this is where we are starting, is the x0. So this means that the convergence for specific problems, it depends a lot where we start. Okay, so now we should also remind ourselves that we are dealing with, we could even have a round of errors, etc., because we are using very small steps in the way that we define the x0, and then probably this x0, if we insert this specific value of 3.65 in this derivative, I'm not sure what this is, but you can work on your own and see or try to understand why at these specific values we have such high oscillations of the possible solutions once you insert this 3.65 as an x0. Okay, so now with all of these discussions, this was just something to go over one of the questions to the homework. We go back to the problem of the ill conditions of a matrix. Now, ill conditioning of a matrix, it is called whenever the solution is strongly depending on the precision of the beam. So let's assume that here we have these two matrices which are shown. Let me see what is the next slide. Okay, Iterative Techniques. So allow me just to so with the ill conditioning of a matrix. Now, many problems in engineering, they are written in the form of a matrix. I think we have expressed this one before, which are in this form: AX is equal to B. And now, many problems in engineering, if they are written in this form, since this is engineering, this is not some complex situation, we want the solutions to be real numbers, okay? Because real numbers, they represent an experimentally measurable quantity. So if you go to electronics lab and you want to measure if you want to measure the voltage and the current, you want to get something which is a real number, okay? But in fact, if you want to check the phase of the potential, phasm and potentiality, then that's a complex number, and that's the only case when you might be expecting complex number. But if you go to problems of civil engineering, okay, so they want to measure the statistics of several walls. So if a building has four floors, just in the case of a kaderkate, each floor has a coefficient of like a spring system, and whatever they want to measure out of it, you expect to get a real number. If we want to get a real number, that often happens if A is symmetric. Okay? So I'm just saying that in principle, when we're trying to solve a problem, if it is symmetric, it's a good matrix. When I say good, this means that also all the eigenvalues are real numbers. Okay. Even a matrix that is not symmetric, it might have all the eigenvalues as real numbers, but for sure, if it is symmetric, this is a given. This is directly implied by this condition. And then A can be symmetric, we want to solve it, but we also know that the solution is, if the determinant of A is different from 0, we get a unique solution. Okay? Only one solution, which is something we are happy about. If the determinant of A is equal to 0, we have if the determinant is equal to 0, what is the possible answer here? Would we have an infinite number of solutions or no solutions? In this case, we have to look for the B. We have to look at this vector, okay? Depending on how B is, look at B. And actually, when we say look at B, we're looking at this. If rank of A, if this is equal to rank of AB, sorry, the rank of AB, then we have an infinite number of solutions, okay? So we can have, but in principle, I can say, so that's something that you can keep it as a node, but I want to categorize something. So we say that the determinant of A is equal to, is different from 0. That's good, we have a unique solution. So the number of solutions, it's 1 actually, okay? If the determinant of A is equal to 0, we have an infinite number of solutions, or we have 0 solutions, no solution, okay? So we can ask a question, is it possible for a linear systems X is equal to B, can we have exactly 2 solutions? Can you answer this? The question is this: is it possible for any system AX is equal to B to find 2 solutions, where the first solution is x1 equal to something and the second solution is x2 equal to something? Can I have an answer from you? You can open the microphones and say a yes or no. You can even, no, okay, thanks, I got them. You can even write here in the comment section. So KD, you are saying no, okay. Any other answer? A no can be a 0, a 1 can be a yes. So you can put in the chat sections, you can enter a yes or no, or 1 or 0. The question is on the board. Okay, who is going to save us some time from waiting for the answers? We need at least another one. So far we have a response rate of 2%, okay? KD out of 47. Okay, no, okay, we're getting a few no's. No, okay. No, 0, why? Why can we have 2 zeros? It's like in the Hollywood movies, they say that they were good guys, but they went too far. And then the good guy says, why can we go too far? And then here one can say, why can we have 2 solutions? Well, the reason is that we can never have 2 solutions because actually we have only 3 possible cases. So we have either 1, infinite, or 0. Okay? But, we can even, you are right, we can never have 2 solutions. So that's one categorization of the problems. Now, let's say that whenever we have these 2 cases, unique solution or an infinite number of solutions, we call the system consistent. Consistent, it means that we have a solution. When you have no solutions, no solution, we call this one inconsistent. But now we have also another specific type of problems when the determinant of A, this is much smaller than 1, which means that this is equivalent. We can say this whole thing is equivalent to stating that the determinant of A is equal to some epsilon, some very small value. And we call this one ill-conditioned. This is consistent. This has a solution. Okay, it's fine. We can get a solution. It is consistent, so it belongs to this category. So we have here, let's say, why can we have 2 solutions? Because so this is consistent, and these 2 top ones, these are also consistent. This is a specific case. And now, what this means, this problem will be called ill-conditioned. This is ill-conditioned. And with this ill-conditioned, what this means the following. If we have AX is equal to B, any small change in any one of the parameters, so let's not forget, in such a system, the input is A and B. Okay? This is a given. What we want to find, this is find, so the questions often are this, find X. And in many engineering problems, we want to find X, which if we use different techniques, we want to find X, which the overall distribution, or if we draw the histogram of these X's, let's say, this is the histogram, X, all the possible solutions that we find, let's say they're going to be centered around X0. And all of the solutions, all of the measurements can have some distribution. Often, we might expect this to be a Gauss distribution, and we want this sigma, the standard deviation, as small as possible. Okay? Let's say that this is a number. Well, this one would be as small as possible. But in these cases, unfortunately, this X0, this does not have such a small sigma, but it can be like this. And imagine now an engineer that is trying to get some correct result, but he doesn't know where to get the X0 out of the measurements. Should she get something here, here, or here? So, and for sure, any measurement that we do is going to have some sigma. We don't have sigmas only if we are working in a perfect world, or if we are working only with integers. Only integers have an infinite degree of precision. So we write a 5 on a computer, it's infinite precision. But whenever we write a pi, it depends on whether we write a 3.14 or 3.1415 or 3.141529, whatever. So we have this problem. But now, whether we write the pi as 3.14 or 3.1415, If the problem has this type of problem, it will have a huge difference if we choose this one or this one. So these types of problems, they are very sensitive to the precision, to the round of error. We know that we are not working always with integers. In any systems, we can always get some irrational numbers. Even rational numbers are good, because rational numbers, they can be written as the fraction of two integer numbers. But any irrational numbers, which are often might appear, we will have that problem. Now, we can use different techniques to quantify the fluctuation of the x. For example, let's say that we change a little bit the b, and this problem ax is equal to b. We can also write here ax plus delta x. This is b plus some epsilon, okay? So let's assume that this was the system, and we change a little bit, we put some perturbation in the b. And this perturbation in the b, in the answer vector, we add some epsilon value, okay? That's something that we are changing, allow me to take this out. And then we try to solve this one. We get here ax plus a times this perturbation. But this is a result, okay? So the idea is that this epsilon in b, this implies this change in x, okay? The only problem is that this epsilon in b, this can be 10 to the power minus 4, but the change in x, this can be 10 to the power 2, okay? So this means that a small change in here, this can induce a huge change on this other side. But if you want to quantify or to get a feeling of how these errors, round of errors, how they propagate in these kind of systems, we can write here ax plus a times delta x. Let's not forget, this is a vector, this is a vector, this is a matrix, okay? This is a matrix. Vector here, this is a vector, and this is also the perturbation in the vector. Okay, so let's not forget this. And this would be equal to the b plus this permutation, which is, and this permutation, let me write this on top of this one. This can be something like, the b can be changed by 10 to the power minus 5, 10 to the power minus 4, 10 to the power minus 3. So this is how much we might be changing these. And then this, we can cancel out with both sides, and it looks like if we want to find how much the error in x is going to be increased because of some perturbation in b, this can be quantified like this. This would be a, this is the matrix, the coefficient matrix, times this vector in x. This would be equal to this infinitesimally small perturbation or fluctuation into b. So now, if we know that the change in b has some quantity, this would be what's the name? This would be the unknown in this case. Okay, if you want to find this one, how much it perturbs. Now, let's try to look at an example. We did some small review regarding the solution of linear systems. And let's have a look if I can find any ill-conditioned example. But I think we had it here on the slide. So here on the slide, we have two. I'm looking at the slide here, but probably 2, 1, 2, 2, 1, 2, and 1.001. This is x, y, and this is equal to 3, 0. So this is ax is equal to b, and here we have another system which is 2, 2, 1, 1.002. So let's change very little this number. Okay? Only one element in the 2 by 2 matrix, and this is times xy again, and this is equal again to 3, 0. So we want to know how much does the answer vector here change if we do this minimal change in here. Now we can do this one on the board. It's easy. When I say it's easy, we can have here 2x plus y. This is equal to 3. Then the other equation is 2x plus 1.001y. This is equal to 0. So we can subtract both equations, I guess, or we can subtract like this. 2x minus 2x is gone. We have y minus this. We get minus 0.01 y. This is equal to 3. Okay. So then we can find the value of y, which would be a negative number. Y would be equal to 3 over with a minus 3, 0.001. So this is y, and then if we would write the equation for the second equation, for the second set here, this 1.001 would be, sorry, this would be 2, and then the answer here, the other answer would be minus 3 to the power divided by 0.002. Okay, so the first answer here, 3 divided by 10 to the power minus 3, it's equal to 3 times 10 to the power 3, so this is equal to minus 3,000. Okay, but here the answer would be 3, this is minus 1,500. Okay, so we can see that only in the y we have a huge change. Probably we don't need to solve this one. Let's see. So the complete answers, this is how they would look like. You should not. Okay, I could solve this one using Octave just to see the answers, but maybe it's. Is 2, 1, so we can say here is 2, 1. The other values, they were 2. So this is A. The B, it can be equal to, this was 3, 0. And we can try to find the answer. So this is the answer B. The coefficient matrix is A. So the answer is this. Then out of, let's write, actually let's do it like this. A1 is equal to A, and A1, 2, 2, this is equal to 1.002. So let's do this again. X1 is the solution of the coefficient matrix A, and using the B as the answer. And X2, we can use the. So you can see how much different these two answers are just by changing 0.1% of a single coefficient in a single number in a coefficient matrix. And the reason for these two is that the determinant of matrix A, it's 2 to the power minus 3. Okay, that's the epsilon, it's very small, and that the same one, this is 4 to the power minus 3. Okay, these small determinants, they are not the same as having the determinant equal to 0, because if the determinant was 0, then we would have that we had no solutions or infinite number of solutions. But determinant being epsilon, that means that we get a consistent system, just meaning that we have a solution, but the solution is very depending on the round of errors. Now, this is what we are presenting. I think we're looking at the screen. Yes, we are. So the next topic that we want to, so this is all regarding the theoretical part of the of solving systems of equations using direct techniques. Now, direct techniques, this means that if we have a system which is 3x is equal to 6, what is x? Is 6 over 3. Okay, that's a direct technique. But we can find the solution also by using iteration methods. And regarding this, let's assume that we have. Let me have a look. Let me find my notes. So the direct techniques that we want to propose now, they will look like. Let me see what part of the board you are seeing. Okay, I need to go back here. And this is it. So, not here. So the matrix equations, the way that we write them, they are such that we have A11, A12, A13, A21, A22, A23, A31, A32, A33. This is the coefficient matrix. And actually, I want to ask you something to help me with something because we have to record the attendance. So if it is possible, all of you that are now in the class, you are obliged to press 1 in the comment section so that they can go over this comment section and to enter the attendance that you were present in this class. So please do that. And so assume that I'm telling this in the class. If you don't have a 1 in your session, sorry, that's a mistake. That's what should this be? This is x1. Well, let's write this one here. This is x1, x2, x3, and this is b1, b2, b3. So this is the system of equations. So please, as I said, please do enter a number 1 in the comment section. Okay. Now these equations, we can write these like aij, any aij, where if we fix I, because whenever we get an equation, the equation goes, let's assume that we pick the second row. We fix the I, this is aij, times xj, okay? So I is fixed, j is interchanging, that means that we're changing the columns one by one, we get this, and this is going to be equal to bi, okay? This is bi. So to get b2 in the second row, we use, so let's assume that we have I is equal to 2, and j is equal to 1 to 3, okay? So this is actually the system of equations. So this is a matrix, vector, vector. So the first method to write a system of equation is this. The second method is this. The third method is this. They are all equivalent. You can write this and save some space in the board. But one thing that we need to enter to include is that this is not all. We have to include that I is equal from 1 to n. So we have to consider, in this case, we have to consider when B1, B2, and B3. So we get all of these, okay? So these are all equivalent, but we have said before in this class that if we see this, what this really means, this is we are summing over b epsilon, b over j. So this is exactly the same thing. If you are summing over the j from 1 to n, And this is Aij times Xj. This is equal to Bi. Okay, change this. So if we want to pick out any I, so from this expression, so again, this is exactly the same, but actually maybe this is better because this notation that we wrote here is included in this summation. But in principle, this is what it means. So for a moment, let's take out the value Aii times Xi, and this would be equal plus the summation over j, which is from 1 to n, but we have to exclude the j, so we have to exclude when j is equal to I of Aij xj, and this is equal to bi. So out of this, all of these three terms that we have here, we just took out the one, but we took out the one that we want to identify. So this xi now that we have here, we can write this one as xi, which can be xyz, xi. This should be equal to, first of all, let's take all the summation to the other side. Okay. So this is going to be equal to Bi minus the summation of Aij xj. Okay, and then we divide by its own coefficient, 1 over Aii. So this is the equation that can be used for the iterative technique. And now, I guess, even when we use the iterative techniques, which was when we used to write a function in the root finding, we used to write y, it was equal to g of x. Okay? We're just ne po mundoheshim të gjeni një formulë për cilën mund ta shkruajmë si funksioni vetvetes, because this way it will correct itself. Even here, this is the iterative expression that can be used to solve these equations. Okay? So now this is called the Gauss. Actually, this solution, this can be called Jacobi method with only a small trick, and Gauss-Siedel method. Gauss-Siedel method. They are very close, very similar to each other, only that the Gauss-Siedel method, let me think for a moment. When we use the Jacobi method, the memory allocation, it uses, let me explain it this way. So let's say the Jacobi uses x0, y0, z0, okay? So this is the initial value for the iterative techniques. We know that whenever we have an iterative technique, we should have an initial guess, and then we use again and again this value of this updated guess, and we expect that this solution to converge to the real root. Now, the Jacobi method, this uses 3 cells to save the initial value, and then it finds x1, y1, and z1. So it uses also three cells to save these quantities. Okay. Now the Gauss-Siedel method, what it does, once you have this x0, y0, and z0, when this one is going to, this uses only 3 cells to save these quantities, because the moment this does not save old values and new values, the new value immediately overrides the old one, and this brings a faster convergence of a system. Now, all of this discussion it's worth if we go over solving an example, and let's try to find an example here. See. So let's use, I guess this part is clear, and I hope if we go over carefully in this example, we understand all of how this iterative technique can be used. So first, let me see if we have anything on the slides. Well, you don't see the slide for the moment, I think, do you? Stop presenting. Oh. Sorry, are you seeing the slides or are you seeing the board?
We're seeing the board.
You're seeing the board, okay. Okay, because here I see that you are not seeing my screen, right?
It's open. We can see the slides.
You're presenting, stop presenting. But then I want you to see what I'm writing on the board actually. Okay. So let's try, let's see an example. Let's try to solve the following. We have 4, minus 1, 1, minus 1, 4, minus 2. 1 minus 2, 4. And we have here x1, x2, and x3. And this would be equal to the vector 12 minus 1, 5. 12 minus 1, 5. So this is a system, and we want to solve this. So if we are to solve this system in using the direct method, how are we going to do this one? We can use the Gaussian elimination and all what that we have learned so far and so on. But now let's use the iterative technique, and let's use the formula which is written here. So this means that, for example, we can say we start with x1. x1, it should be equal to, let's look at this expression. x1, let's multiply the first line. This is equal to 1 over 4, okay, times, this is bi is 12. So this is 12 minus aij. So aij is the next element, minus 1 times x2 minus 1 times x3. So how do we get this? Let me write this just for a moment. So we have here 4x1 minus x2 plus x3. This is equal to 12, okay? So it is obvious that this is the first equation that we can get from here. And then what we are trying to do is that we keep this term here, we do 12 minus these two terms. You see these two terms, we throw this on the other side, so these go here, right? And then we divide by 4. So I hope that this is clear here. And so allow me to erase this one. So this is what you get for x1. But now this is an iterative technique, and let's use, first we have to use an initial value, an x0. So even in when we try to find the roots of the system, when we're trying to find using the Newton-Raphson method, the first thing that we did, we assign an x0. In this case, let's assume that this x0 vector, let's give 0, 0, 0. Let this be our starting point. And then here, in this expression, if we use this, if we substitute here the zeros, we get 12 over 4, we get x1 is 3. Okay, so this is, if it is Jacobi, this is 0, 0, 0. And x1 prime, we got 3 here. We get 3. So we find this. Then the x2 is going to be equal to, x2 is equal to, again, 1 over 4, because this is the b in front of it. 1 over 4, we have b2, it's minus 1, so this b2, it's minus 1. Then we have, if you take this minus x1 from the other side, it's plus x1. Or let's do it like this, minus 1 times x1 minus 2 times x3. So this would be the expression. Now, if we use the Jacobi method here, what we will have here, sorry, I wrote this one x, y, z, but let this be x1, x2, x3. Now, if we use the Jacobi method, this will be minus 1 over 4, because x1 and x3, they are still 0. This would be minus 1 over 4. Minus 1 over 4. But if we use the Gauss-Siedel method, if this is 3, the Gauss-Siedel method, this has overridden this one already, and this value 3 goes here immediately. So if it is Gauss-Siedel method, the y, it will not be a quarter, negative a quarter, but it will be, this is minus 1, plus 3 is 2, 2 over 4 would be 0.5. Okay, so again, you can solve this one on your own. Let's check the solution. So this is 3, this is minus 1, plus 3, it's 2, 2 over 4 is 0.5. So Jacobi would have this order. This would be the other way. Now, x3 would be equal to 1 over 4 again, because this is the A. So when I is 3, this means that x3 is equal to 1 over A33, which is 1 over 4. Bi, what is B3? B3 is 5 minus 1. Imagine that we will take this term to the other side. Minus 1 times x1 minus 2, which is this coefficient, times x2. This whole thing, this would be equal to. Now, allow me to write here 0.5, assuming that we are using the Gauss-Siedel method. Okay? If it had Jacobi, we'll not update it. But now we found this x2, and this x2, assuming that we are using the Gauss-Siedel method, where the new values we write them immediately, this x2 will be updated here. And this expression, this would be something like this. This would be 1 over 4 times 5 minus, this is minus x1, it was 3, minus 3, but wait a second, yes, it's minus 3, and then minus 2, this means it's plus 2, and x2 is 1 over 5, okay? So this is equal to 2 over 2, that's 1, 5 minus 3, 2, 2 plus 1, 3, it's 3 over 4. 0.3 over 4, 0.75. So here, this is 0.75 is the x3. If we use Jacobi, if we use the Jacobi method, this will be still 0, 0, and this x3 would be 5 over 4, 1 point, what is 5 over 4? It's 1.25. Okay, so this is this would be the relative difference between these two. So assuming that we got this part, the next thing that we need to do is the following. We need to check how much different is this new solution. So we started from 0, 0, 0. Okay, or we have written this here actually. So, and we want to check how much error do we have from this iteration, the initial one, to the next one. And the error that we need to calculate is the following. We do 0 minus 3 absolute value divided by 3 times 100%. Right? This is how we do this, which is 100% difference or error, which is huge, which means that we need to run the iteration again. Okay? And then if we do this, we substitute, so we found all of these values in one round, and let's see what is the next, what are the next values. And then here we'll have the following. X1 would be equal to 1 over 4, 12, plus, so minus is plus. What is x2? x2 is 0.5. I'm reading it from here and from the column of the Gauss-Siedel. Minus x3, which is 0.75. Good. So this x1, it's equal to 2.9375. 2.94. Let's add this 2.94. So we can write here 2.94. And then we go to x2. x2 is 1 over 4 minus 1, because this was b2. Minus is plus, so let's do this one. Plus x1. x1 is 2.94. 2.94 plus 2x3 plus 2. x3, it's still 0.75. 2 times 0.75. And this whole thing, this is equal to 0.859. 0.859. Okay, so we write this one 0.859. That's good. And the x3 will follow the same way. x3 would be equal to 1 over 4 multiplied by 5 minus 1, that means minus x1. x1 is 2.94. 2.94 plus 2x2 plus 2, why do I, oh, okay, this plus 2 appears twice, plus 2x2, x2 is this value, 0.859, 0.859. If we substitute all the values, we get a value of 0.94, 0.945, okay? So we started with 0, 0, 0, we get this, and now this. So this is 0.945. Okay, so this is how the Gauss-Siedel method works. And now that we find this, the next thing that we need to immediately do is to calculate what is the error. The error is calculated like this. 3, we take the absolute value. Okay? 3 minus 2.94 divided by the new value. Always the error is calculated using the new value as a reference. So we divide by 2.94. We don't divide by 3. And we multiply this by 100%. It looks like this value is going to be some relatively small value. It's 2.94. 3 minus 2.94 is something like 0.06. 0.06 divided by a number which is approximately 3. Okay, if you have a calculator using, you can immediately find what this error is. But we get 6 divided by 3 times 10 to the power minus 2 times 10 to the power 2. Okay, because this is 100%. And this is equal to 6 divided by 3, it's 5. 5, it looks at times this, 5%. So it looks like we get a 5% difference. So from the first root, so assume that we don't have the column of Jacobi here. From 0, 0, 0, we got 3, 0.5, 0.75. And the error of this, with respect to this, it was 100%. But now the error from here to here is just 5%. Okay? Probably it's not 5%, it's something less, because we divided this by 3 just to get an approximate value. So this is an approximately 5%. Probably it's going to be something like 4.5 or 4.7. Okay? But this is the error. And then, if we are not happy with this error, we continue another iteration. And we hope that this system is a converging system. Because the direct method and the indirect method, they have their issues. And the major issue of the iterative technique is that probably it does not, it never, what's the name? It never converges. It might not converge. Okay? But as we are going to see, a system will always converge if it is diagonally dominant. Diagonally dominant, it means that the diagonal terms are larger than the sum of all the rows. If we look at this system that we have written here, these 4s are larger than the summation of the absolute values of all the other matrix elements. So if we have a look here, let's see what we have put on the slide, but I have to cancel this present stop. Oh, I have to present right there. Anyway, this is the same thing. I could have written it on the board for sure. And this expression here, which states that AII is larger than all of these terms, summation of, again, AIJ. Let me stop presenting. So a system, it converges. Let me see. We use this part of the board. So it looks at with 2 iterations, with a small number of calculations, we found an error of less than 5%. Now, the diagonal dominance, this is defined as the AII. This is larger than the summation, than the absolute values of AIJ when I is different from J. Okay? So if this is true, then we have this the diagonal dominance. So in this case, we have to use the absolute value, okay? Otherwise, it might be. So in this case, when I is equal to 1, we see that A11, this is larger than the summation of absolute value of 1, absolute value of -1, plus absolute value of 1, which is 2, and this 4, this is larger than 2. Sorry, larger than 2 here. So this is good. So if this is the case, we call the matrix as diagonal dominant. So this would be the diagonally dominant system. Okay, so this is how we go after the. Let me try to determine. I really don't want to erase this part, but let me use this section.
Break.
Now I have a question for you, which is the following. For the matrix which is given here, A32 minus 6, 0, 7. Is this matrix, if we have a system where this matrix has the coefficients of the equations, would this converge if we use iterative technique? We have 2, 4, minus 1. Would this converge? Which you can answer this by looking at whether this is diagonally dominant. And also we have this other matrix 1, 1, 5, 1, 4, minus 1, 3, 1, minus 1. So any answer? Let me see. Are you answering it on the chat section? Okay, I get an answer here. It has a 0 in the diagonal. Okay, that's also an issue. Thank you for your answer. So it looks like this would not converge. But can we do anything for this to converge, or how can you use this one? So any suggestion here? So what we can do here is that we can interchange row 2 with row 3. Okay, let me see. Add the rows, switch rows. Okay, I got two options. Ignatius has a more original proposal. He's saying to switch the rows. We can add the rows. You are right, Katie. Okay, you are right. We can do it. Nothing will change in the system. But if we add these 2 rows, then we have to add also the rows of the B on the answer vector. We are aware of that. I think we know that. So we don't change only the coefficient matrix, we need to change also the B. But in this case, probably interchanging row 2 with row 3, it might be enough. Because if we do that, here we have 2, 4, minus 1. The 4 would be here, and the 7 would be here. Okay? And then it would be Let me try to, so the 4 would be here, the 7 would be here, and then the updated matrix would be diagonally dominant. So the red colors would be the updated versions. And also here, this also, it looks like a system which it's not going to converge if we use an iterative technique. But if we switch row 1 with row 3, here we get the 3 here and the -1 here. Okay, and so it's not easy to read it this way, but probably I think it's obvious that exchanging row 1 with row 3 would make this one again a diagonally dominant matrix, which means that this will converge. Now, let's have a look at the. Actually, it's also think also about this matrix here. -1, 3, 5, -2, 4, -5, 0, 2, -1. So let's assume that we have this matrix and the B is equal to, I think I'm on the borderline of your visibility. So let's assume that the B is equal to 7 - 3, 1. 7 - 3, 1. So let's have a look at this system. Well, can we do anything to make this a converging matrix? So this is the matrix A, and the answer vector the B is shown here. So will this system converge? That's the question. And for this, it looks like, do we have any answer? I mean, any idea? Any guess? Okay, Bjorn. Yes, Bjorn. I see switch rows. You know, let me give this as an exercise for you, and this will be the first thing that I'm going to ask you next time. Assume that the B here for this exercise, I will give a break. This is 12, 1, 5. Here, the B, it's equal to and please have a look, and this is the third system. See how they converge. In this case, we assume that they do converge, and check whether the system converges at all. So you can do any change of matrices, but check this one. Okay, so for today, we started the class, we discussed the iterative techniques, we solved a couple of examples using the Choleski decomposition and other decompositions, and we explained also the diagonal dominance of a linear system of equations, which is reflected in the property or in the values of the coefficient matrix like here. If you have any questions, I can receive those. Do you have any question? Okay, let me see if you are including your questions in the, maybe, what is this? Maybe adding rows in this case. Arion, which one? In the third case, you mean, Arion? Okay, can we multiply by -1 both first and third rows? Let me think. Actually, multiplication by a constant number, it does, so the multiplications, we don't like it that much, Arioli, because it's not an elementary row operation. The operations that we are very happy to have is the exchange row I, you can exchange with row J, and then we can have also row J star is equal to row I plus lambda row J, or sorry, rho I. Now, multiplication by a negative 1, then, yeah, I think you can do that, of course, you can do that, but you have to multiply also by -1 in here. But if you multiply by then by -1, yes, you can do that. If you multiply it by 1, but can we get the diagonal dominance? That's the question. There may be some doubts on this becoming a diagonally dominant matrix, because in order to figure out or to predict the possibility of being diagonally dominant, one thing that we can do is that we can determine the values in each row which have the highest absolute value. Now, these are the ones. Now, we observe that even this is not diagonally dominant if we put this in the third row, because here we get 6 compared to 5. It's not, you cannot make it diagonally dominant. This, it looks good. This can stand in the third row. This is good. This can stand in the second row. But what are we going to put in the first row? Okay, we don't have a good candidate, a number, a coefficient which is larger than the sum of the absolute values. Nathaniel? Okay, Nathaniel. Okay, the chapter in the book, the iterative techniques, allow me to have a look. So, I think the iterative techniques is something like chapter, the Choleski decomposition, they are, so we have chapter 10. You are responsible to read chapter 10, but I guess if you go over the textbook and the iterative techniques, they are in chapter 12. So today, you can read from chapter 10, 11, and 12. So the iterative techniques, they are in chapter 12. Okay, if you don't have any more questions, so look at these last exercises that we left it as an exercise for you. But chapter, Bjorn, allow me to have a look. So chapter 7, 8, 9. I don't remember, well, chapter 7, 8, 9. Can you have a look what topics are in these chapter 7, 8, 9? I don't have the book with me. Bjorn, can you have a look what are the topics in there? I think we have the roots of equations there. Bjorn, can you have a look at this chapter 7, 8, 9? What is the... Well, I don't have the book with me, Bjorn, but I'm going to... polynomial. Okay, root of a polynomial. Check this in here. Okay, studies roots of equations. Let me have a look. Let me have a look at the. But it might take some time to me to look at the chat. You know, 9. Okay, Gaussian elimination. So now 9 is for sure it's included because it's Gaussian elimination and all of these techniques. Thank you for including this. That's also a question. I really let me check. Let me look at the PowerPoint slides. So in the PowerPoint slides of the last 2 weeks, we had chapter 7. Chapter 7, I think we did chapter 7, but we just went briefly over it, and we had the notes in the PowerPoint lecture notes, okay? 8 and 9. So we are responsible for 8, which is linear algebraic equations and matrices. 9 is Gaussian elimination, yes. So you are responsible for all of these. But from chapter 7, it's not a very long chapter, but you are responsible to look at the Gaussian golden search, which is to search for the minimum or the maximum of a specific function. So yes, now that I looked at the lecture notes, you are responsible, yes, for 7, 8, and 9. But 7 is a short chapter, and read only for chapter 7. Check only what you see on the slides, okay, on the PowerPoint. Okay, 10, 11, 12, let me have a look. Check only slides for 7. Now let me have a look again for 10, 11, 12. Okay. 10 is LU factorization. Yes, 10 you are responsible. Siedel. The chapter 11, you just, from chapter 11, focus on what we covered in the class, okay, which we discussed the ill conditioning of the matrices. That's all you need to extract from chapter 11. And then from chapter 12, we have the solution using Jacobi method and the Gauss-Siedel method, okay? So I would strongly suggest to go over, so now that I'm looking at the slides, or at the lecture slides, just go over the lecture materials or the slides that I share with you, okay? There are some sections in the textbook that we use that might be like, we don't go over those. So, Denado, check on this. Yeah. Denado, you have a question. You said you're going to go over 6 chapters. Yes, you'll go over 6 chapters. But the chapters are not... So, for example, if you look from the textbook composition, probably it looks like a lot of material. But if you go over the slides and the class recordings, you might be more to earth, okay? It might be easier for you to determine that they are not very difficult. And then if you have any question, you can always come back with emails or anything else. Aniledio, you are responsible for all the material that we have covered in the class, okay, in the recordings. Of course, I try to keep everything in the same, yes. Even the slides, I try to adapt them to keep all the material in the slides and in the class recordings. So yes, you are. You are responsible for those. You can say that. Any other question? So the class is over for today. I can just... yes. And I hope... Well, për këtë metodët e gjetjes së rrënjës, për këtë Newton Raphson është shumë klasike, këtë duhet ta shikoni, false position, kemi përdorur dhe metodë tjetër, second method, kemi përdorur sekantin. Devi, okay. You know, I can send you, yes, I can send, mund t'ju dërgoj një listë që do të them ato seksionet në çdo kapitull që kemi përmendur. Patjetër Devi, në rregull. Edhe për pyetjen e Denados, është metodat e gjetjes së rrënjës në klasë, unë harroj si kemi bërë gjitha, por kemi bërë Newton-Raphson, kemi bërë FPI, kemi bërë edhe këtë second method, sekantin, metodën e sekantit. Dhe nuk e di kemi përdorur gjë tjetër, se se mbaj mend. Metoda ka shumë, mund të kemi përmendur një të katër për root finding, por besoj se kjo është shumica. Por edhe për këtë pyetjen e David, do i çoj një listë ku do specifikoj kapitujt edhe seksionet brenda kapitujve, që të paktën i kemi bërë me do e mos. Në rregull, në një pyetje tjetër, nëse s'ka pyetje, ne mund ta mbyllim klasën. So if you have any question, please you write or you can communicate with the microphone. Mirë, më keni faleminderit. Atëherë nëse kemi pyetje të tjera, ju faleminderit për vëmendjen. Dhe ju uroj gjithë mirat.